that last video ended kind of abruptly um, uh, because I was trying to fit it into my 15-minute time limit. Hopefully, you see why we use the 1/2 um, right here, and how it canceled well with this stuff here. All that matters when I'm dealing with these polynomials is what the biggest power is in the top and how it compares to the biggest power in the bottom. If, for example, I had a 4 here, man, there it goes again, and a 3 here, then I would have gotten a limit of 4/3, and that's okay because that falls into the whole being something other than 0 or infinity. So it didn't have those guys, so I'm gonna erase it. Boink, 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 and I'm gonna come down here and we're gonna do one more. So this last one, sigma n equals 1 to infinity of 3n plus 5 all over n times n plus 1 times n plus 3. For this one, I would like you to look at the degree of the top and the degree of the bottom and think to yourself, what what function or what series am I going to use? What p series is going to work with this? Hopefully, you said 1 over n squared. It works great. How do I get that? Well, the denominator in the bottom would multiply to n cubed here because n times a n times a n. And the top is a 3n. And I actually don't even really care about this. I just care about the n and the n cubed. And what's that give me? 1 over n squared. So that's what I take here. So let's set up our limit. L equals limit as n goes to infinity. A lot of times I will write, well, I'll write a, whoops, come on, this thing's so frustrating, a sub n over b sub n. And then what I'll do is I will write this piece right here, which is 3n plus 5 over n times n plus 1 times n plus 3, close, and then I'll do my copy dot flip right here. I think you should see that like that step's going to be the same every time, so I'm just going to multiply, whoops, not 2, I did that backwards, n squared over 1. And then this thing, notice I've got n cubed in the bottom, and I've got n cubed in the top, but there's a 3 on the top. So this limit is actually 3. So this goes back to the one that I said earlier, and it's fine to evaluate those limits like that. You don't have to use Hopital's rule. If you have a polynomial on the top that's got the same degree as a polynomial in the bottom, the limit is just that number. So we got 3. So this goes back into our definition. Boom. Is it 0? Is it infinity? It's neither one of those. So what's that mean? They do the same thing. So what we can say after this, and I know I've like structured the way I've said this a couple different ways so far, so I'm going to do it a little bit differently again, right? So what I'm going to say here is sigma n equals 1 to infinity 1 over n squared converges by p series, parentheses p equal 2 greater than 1. So come back. Where is it? Call it S sub infinity. Do that every time. S sub infinity also converges by LCT. So I hope you're feeling good with this. I hope that you see that it works really well with any of these functions where we have polynomials in the top. You could actually use LCT with a lot of things, and instead of using p-series, use geometric series, but we're actually have a better tool for that later. And I wanted to say one more thing, so hold on one moment. This here is one of our charts, images, whatever you want to call it, from when I taught you nth term, integral test, and p-series. I have LCT and DCT in this box here. I'm going to highlight LCT because we've now learned LCT. And I guess we should highlight geometric because we've done geometric series. We need to practice a little bit more with them, I think, but you've done them. I've decided that at this point, I'm going to leave DCT out. DCT stands for direct comparison test. And as far as everything that I've ever seen with this stuff, DCT works with a lot of the works with about works with the same type of problems that limit comparison does, except for it only works for about half as many problems. So in that case, I think that LCT covers almost everything we would ever need for DCT. So given the situation that we're in with a really crunched timeline this year, we're going to do LCT. And then the next thing we're going to do is focus on the ratio test and pulling back to not just when does sigma of a sub n converge or diverge, but going back to this problem from a couple days ago, where we had f of x equal to e to the 2x, and I asked you to find a polynomial of degree 3 that matched all possible derivatives. When I came down here, we did the third degree one, and then we said, you know what? I think we can do the nth degree. And we came up with this nth degree one, and I hope you remember when we plugged that into Desmos and we watched it flip-flop, 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 and it was getting better and better and better. So the question that we really want to answer with this, and this is why we've got all these tests, is when does this series right here match the function for which we are targeting? So when do these things with not just n's, but also with those x's in them match functions f of x, g of x, whatever, that they are targeted to be? And I want you to keep in mind that that is our goal with this. When we're doing all these tests, people sometimes get confused. They're like, wait, what? What's going on? Why am I doing this, right? This is the goal. We want to approximate functions. Tangent lines, they ain't good enough. We need to do better. So, you get with LCT. Hopefully you know when to choose what different series to compare it with, to do the limit comparison with, and I hope you're good with these other 4 tests right here, because next thing we're going to do is rock through some ratio tests. All right, that's all I got. See ya.